Okay, now recording is on. So this is a review of probability and statistics. Okay, so some of the concepts, and also some of the, well, it's just concepts, okay. So when we study probability, we basically trying to study the likelihood of certain outcomes appear when you run an experiment that has randomness in it. For instance, you have a coin and you toss a coin, then it could either end up with a head or with a tail. So then before you toss a coin, you don't know what the outcome. You don't know exactly what the outcome would be, but of course, you know it will either be a head or a tail, assuming you don't, your coin doesn't land on the edge, right? So on the edge of the coin. So either the head or the tail. So that is called possible outcomes. And if you roll a die, and the die, let's say, has 6 faces, then of course, before you roll the die, you don't know exactly what a particular face will land or will be on top, but you do know that you have six possible outcomes. So rolling a die or tossing a coin is called an experiment. Okay, so it has randomness in it because you don't, when things happen, you don't know what exactly the outcome will be. So that's randomness. Right? But then you can put all possible outcomes in a set. Then we're going to give a name to that set. So that name is called a sample space. Okay, so now this the first bullet says a sample space is a set of all possible outcomes of an experiment. Okay, and then any subset of a sample space is called an event. Okay, so of course a single outcome or a singleton subset is an event, and of course any subset would be, so it is an event. So if you have, the size of a subset could be 1, could be 2, could be 3, and could even be empty. So could even be 0. That means that there isn't anything happen, no event. Right? Okay, so for instance, throwing a die with an outcome that is either red or blue. So this is a subset of 2 outcomes is an event. So that means you can actually define many different kinds of events for a sample space. Okay, then we want to measure, right? So we want to measure the likelihood of each outcome would appear. And that is called probability. Okay, so that's what the probability is. So the third bullet says that a probability P maps, again, is a measure. It maps each element in the sample space. So which, okay, each element is just outcome in the sample space to a non-negative value. So that value is between 0 and 1, such that you sum them up, you sum all of them up in the sample space is equal to 1. So we use 1 to indicate something will definitely happen, and we use 0 to indicate something doesn't happen, and anything between 0 and 1, then it has some likelihood to happen, and that is called probability. Okay, so the fourth concept is called probability distribution. So this has to do with the entire sample space. So if we can figure out probability for each outcome in the sample space and put them together, then that is called a distribution or a probability distribution. So for instance, let's say I have an unbiased 6-sided die, then each side has equal opportunity to show up. So that means that since you have 6 possible outcomes, so then the probability for each outcome is 1/6. And you put all of these together, then it is a probability distribution. The probability for all outcomes in your sample space, then that becomes a probability distribution. So for this particular case, our probability distribution for an unbiased die is this. Okay, so it's a set of 1/6 for 6 possible outcomes. So that's, again, so we talk about 4 basic concepts here. One is a sample space. In order to talk about sample space, we have to talk about experiments and outcomes of that experiment. And then we talk about events. So event is simply a subset of a sample space. And then we want to measure the likelihood of each outcome or each event. Then we use a measure, and that measure is called probability. So we use a number between 0 and 1 to represent that likelihood. Okay, so 1 means definite, and 0 means it's not happening. 1 means it happens, and between 0 and 1, that means it has a likelihood to happen. Okay. And then for a sample space, if we can figure out probability for each outcome and put them together, and that is called a probability distribution. So next, we're going to see for another example, for a biased die, excuse me, for a biased die, a probability distribution could be different. For instance, in this case, suppose, let's assume this die is biased, which has more likelihood to turn out red and orange. Okay, so with the probability that 1/3 to turn out red, 1/3 to turn out orange. For the rest of the colors is 1/12, because you know that when you sum them up, it's equal to 1. So this is a probability distribution for a biased die. So from text mining purpose, okay, and we can think of a text document is an outcome of an experiment, and so you can imagine that. So you can imagine that I have, because a text document is just a collection of words in certain way, right? So in sentences, that's also a sequence of words that satisfy grammatical rules. But if you just look at from a straightforward view, you just look at words, then you can imagine these words are generated from throwing a die. So this is a multi-phase die. So how many phases? That's equal to the number of words and plus digits plus punctuations, right? Plus other symbols. So that is a die to generate your text document. So you roll a die to see what what the outcome is, and that's So either the word, either punctuation, then you will put that in your document. So then you can view a document as an outcome of throwing a such die, right? But what you can see or what you can observe is only a partial thing of the entire corpus, so or all possible things you could ever be. So that means that in order to come up with a probability distribution for each word, by just looking at some text documents, right? So that is the task we need to do. So that means that we need to estimate a probability distribution with partial knowledge about our samples, about our sample space, because you can only observe finitely or small number of documents, however that number is. Even though it's really big, you're not going to cover all possible text documents. But from what you observe, then you want to come up with a good estimate of the probability distribution. Okay, the next concept we're going to talk about is called random variable. So before this, we talk about outcomes of an experiment. So the outcome could be, in our case, we use words to represent them, right? Using head, tail for coin tossing, and use colors, red, orange, blue, green, and so on for dice. So we can map these outcomes to a number for easier processing. So in other words, for instance, we can map a head to 1, map a tail to 0. So that is a map. That is a mapping, and that mapping actually is a function, right? So this is a function. So we call that function a random variable. And similarly, you can you have a die. You can map phase 1 to number 1, phase 2 to number 2, and so on. So that is also a random variable. Likewise, in our case, we're dealing with text. You can also think of that you map each word to its natural dictionary order or lexicographical order. And that, of course, is a number, is indexing. So then that is a random variable also. Okay, so that's another view. We talk about these random variables. And then suppose we figure out a distribution of generating words, then each experiment, when you run each experiment, and you simply just generate a word because it has random, it's random. So each time you run an experiment, the words you generate would be different. But still they follow the same distribution. Okay, they follow the same distribution. So then even though that distribution may not be known, right? Because it has a distribution, that's for sure, but whether you can compute that distribution is another thing by having partial observation. So it may not be, you may not be able to compute that distribution completely, but you do know that distribution exists. So when you run an experiment independently each time, it's equivalent to saying that I draw a random variable from that distribution. So that's what this means. So this is the last bullet. Given a distribution theta, write x. So this is a approximate theta to denote that x is a random variable with distribution theta on its values. okay, because a random variable maps some outcome to the value. And we say that X is drawn from theta. In other words, we may think of each independent experiment as a random variable, right? So that's a convenient way to look at independent experiments, right? So from the same, with the same outcome, following the same distribution. So each experiment is a random variable. Okay, so that's why we call that a random variable anyway. Okay, so in text mining, we may think, as I mentioned earlier, we may think of words as outcomes of throwing a biased n-sided die, where n is the total number of words, plus digits, right, plus punctuations, plus any other symbols you may use, such as a $, pound sign, and so on in a corpus, in a corpus of documents. Okay, so that's from text mining point of view. So then this is what we need to look at. So we often want to compute the probability of a word under this theta. So this means that we know that a distribution, probability distribution exists. So assuming under this die, right? So I have a die, either biased or unbiased. Let me think of it as an unbiased die. So under that die, I can generate that word, but of course, usually it's biased, right? So that if unbiased is easy to compute, it's just a uniform distribution. If it's biased, that's much harder to compute, but that's what makes it interesting. So that's what we want to compute. So we often want to compute the probability of a word W under the underlying distribution of words. Okay, and the difficulty is that this probability distribution is unknown or just partially known because it's unbiased. And because it's biased, okay, so we can only obtain information by observing documents. Of course, the more the better, but you can only observe a finitely many number, and then you want to use finitely many observations to infer this probability distributions. So in order to do this, okay, so that's our main task. How can we compute this? So we need to, again, introduce some concepts of probability. In particular, we look at conditional probability and joint probability. Okay, so this has to do with multiple random variables. So let X and Y be two random variables, or you can think of them as two random events, okay, over the same sample space. Then the probability that the event X happens when Y happens is denoted by P of X bar Y. So this means that the probability of X is conditioned on the outcomes of Y. So if Y happens, then we look at the probability that X happens. So that's what this concept is. And then we can look at joint probability. So let's say I have two random variables, X and Y, over the same sample space. Then the probability that the probability that both events happen or both random variables happens or both event happens is denoted by probability of X and Y. So usually the meaning of this is just that I want to know the random variable X, excuse me, is equal to X. So X here is a value, and this capital X is a random variable. And I want to know Y is equal to small y. So I want to know this probability. And that is written as Pxy. So that's a shorthand for this, for a certain value. Okay, so likewise, this is equal to X is equal to small x for certain value. And when certain value small y, when the random variable is equal to small y, so that means that happens, I want to know the probability that random variable X is equal to small x. So that is the meaning of these notations. So the next two rules are important. So we use them a lot. So the first one is a chain rule for joint and conditional probabilities. So we link them together. So you can think of that. Well, actually, this rule is easier. Well, it's actually easy to understand by having the following interpretation. So this is a joint probability that says that both events happened. So of course, that means that the probability that first we look at the probability X happens, and then when X happens, the probability Y happens. So both of these happens. That means that is equal to the product of P of X and P of Y bar X, right? So first X happens, and when X happens, Y happens. Likewise, you can also look at Y. So when Y happens first, and then so then the probability of X happens under Y happens. So that means that these also are equal. So that means they can commute because the order of X and Y is not really important because they just talk about both X and Y happens. So that's chain rule. Okay, so we don't go through a rigorous mathematical proof, but we can just use that interpretation to convince ourselves that's true. Okay, so then from these two, from here, we can derive a very important relations that's called Bayes rule, meaning that if you look at this guy here, so the probability of X happens when Y happens, or the conditional probability of X under Y is equal to the probability of X times the probability of Py bar X divided by P of Y, because you can move the P of Y over. So this guy is called Bayes rule. Now, it looks simple, but it's a really, really powerful thing. Okay, so a lot of methodologies is based on what are based on this Bayes rule. All right. So next we're going to look at how we are going to use Bayes' rule to come up with a to estimate a probability distribution. To estimate a probability distribution, it often means to estimate a parameter or a set of parameters involved in that distribution. Okay, so oftentimes that distribution can be represented by a function of certain parameters. Okay, so either one parameter or more than one parameters. For instance, the first distribution we're going to look at is the easiest distribution or the simplest distribution. That's called binomial distribution from coin flips. Okay, so now let's look at this. So we flip a biased coin n times with theta being the probability of heads. Okay, so this theta is the probability of seeing heads. Then let's say among this n times of coin flips, I want to know the probability of seeing k heads. Okay, so the following is a distribution, but this is how we can think of it. So for each fixed and outcomes of tossing a coin. So for each fix, of course, let's say I have k heads, then of course the probability is theta to the k, because you have k outcome, you have n outcomes. So k of them turns out head, and then n minus k of them turns out tail. Again, we are using 1 to represent heads and 0 represent tail. So this is the probability 1 minus theta, that's the tail. And you have n minus k times. But then this is for the fixed n outcomes. But so that means these heads locations are fixed. But then of course these k locations of head could be on any different places. So the different places, how many of those is n choose k, because you have n places. So n choose k of them. So you put them together, that is a binomial distribution of probability of seeing k heads in from tossing a bias coin n times. Okay, so that theta is what we want to estimate. If you know the coin is unbiased, we know that theta is 1/2. So you have an equal chance to turn out head or tail, so theta then is equal to 1/2. But if theta is biased, if that coin is biased, then theta may not be equal to 1/2. So how do we know what that value is? Right, so that's what we need to estimate. Okay, so this is important in text mining because we really want to know, in many situations, we want to know from observing certain number of text documents, we want to infer what the underlying distribution for these words is. So we start from looking at a simple example. So we have, in general, 2 methods. Okay, so one is called maximum likelihood parameter estimation. We call it MLPE. or sometimes we simply call it MLE, indicates maximum likelihood estimation. And the second is is called Bayesian parameter estimation, BPE. Sometimes people call it BE, Bayesian estimation. So when you see those terms, or you see these shorthands, then you know what they mean. So now let's look at how we're going to use these two methods to come up with an estimation from observing some experiments, some outcomes. So here, suppose we are using maximum likelihood estimation. So suppose we observe a sequence of 3 heads and 2 tails, and the underlying theta is unknown. So somebody use this coin, use this bias coin, with the theta being the probability of seeing a head. Theta unknown, but we can see we have some experiments. So from those experiments, we want to come up with an estimate of theta. So suppose now I have observed 3 heads and 2 tails, so that means I flip this coin 5 times. So then the probability this happens, so this event happens, okay, running it 5 times with 3 heads and 2 tails is theta to the 3 and 1 minus theta to the 2. So that's what we know. And then in order to estimate this theta, we would assume that this outcome is the largest possible probability we see. So which means that we want to maximize this function and then figure out what that theta is. So that means the largest possibility for this to happen is simply to choose theta such that this function, we call it f of theta, is maximum for theta between 0 and 1. So what you do is simply to take the derivative on theta and set it to 0 and figure out what that theta is, right? So in this case, we can easily do this quickly. So we got theta theta cubed, 1 theta square. So we take the derivative on theta, then it is equal to 3 theta, 3 times theta square, 1 minus theta square, and then minus 2 theta cubed, 1 minus theta. So then we set this to 0. So that means we have, I'm going to move over here. So we simplify it a little bit. So we take theta cubed, theta square, 1 minus theta out. So then we get 3, 1 minus theta from the first term. The second is minus 2, got theta, then it's equal to 0. So that means for this to be equal to 0, either theta is 0 or theta is 1. Of course, these are trivial. It's not going to be the solution for theta because it just means that theta is equal to 0 means that when you flip this coin, it always turns out tail. Theta is equal to 1, it always turns out head. But of course, from what we observe is not that case. So the only possible case is from here. So that is 3 minus 5 theta is equal to 0. So then we know that theta is equal to 3 over 5. That's how we obtain this. So this is biased. uh, is a biased coin, and from one observation, we can have an estimate for this probability theta. There's a parameter, right? That probability turning out head. Okay, so that is the maximum likelihood estimation, and you can, for this, you can actually simplify it to the following formula: the number of head over the total number of experiments. So it's quite straightforward that way. You think of that way. All right. So MLE is based on one observation. So what happens now if we conduct a second experiment and we observe a discrepancy? Okay, so the second experiment, it looks different. So then we need to update the prior estimation based on new observation. And the Bayesian's rule now comes into play. Okay, so as a matter of fact, Bayesian rule or Bayesian parameter estimation is a method for us to learn what happens in our world, right? We only have limited observations, so we constantly adjust our estimation based on new observations. Okay, so that is really powerful. That's why it's really powerful. The formula looks straightforward, but the meaning of it, it's powerful because that is the method we learn our world from limited observations. But we get more observations, so we then use the new observations to adjust our belief. In other words, to adjust our prior belief. So then we have the concept of prior distribution, because that's our prior belief. And then based on new observations, we come up with a new estimate, and that new estimate is called posterior distribution. That's the adjusted belief, right? We have prior belief, we have new observations, then we adjust our belief, then we come up with a posterior belief. So that's a Bayesian parameter estimation. Very powerful. So again, we rewrite that Bayesian rule in a slightly using different variable name. So here theta is what we want to estimate, and D is our observed data or observed outcome. And we have a prior belief, P of theta, from previous observation. We come up with P of theta. So this is called prior distribution. This is the current observation, assuming that theta, right? Because the theta is always there that govern this coin. We just don't know what the exact value of that theta is. But now we have a new observation. And then that's our new theta value under this new observation from prior belief obtained from prior observation. That's how we can come up with this the posterior distribution or the adjustment to this theta. And P of D is a constant, okay? Because this D is what you observed. So in other words, P of D here is the summation of all possible value, But since this all possible value will be continuous, right? Theta is just between 0 and 1. So we're going to just say 0, 1. P of d theta prime, P of theta prime, and d theta prime. So you just sum all of them up. So that's P of d. So it's, for each observation here, you think of that as a constant. So then, now let's look at this. So P of theta is a prior belief, meaning that's what we learned from prior observations. And D is a new observation, and P of D is the current, is the likelihood of the new observation. We call it likelihood. P of D is the marginal likelihood of D, because you have to consider all possible values of theta. You sum them up, so that's called marginal likelihood. And P theta, bar D, is the posterior distribution or probability of theta. That is adjustments on the prior value of theta, the probability of theta. Okay, so that's the meaning of it. So now with a new observation, how can we adjust this theta? So then, let's say, for example, we know from the prior experiment, we have theta which is equal to 3/5, which maximize theta cubed times 1 minus theta square. So this is our prior observation. So then our we need to come up with a prior probability on theta. So that, of course, is a distribution, and that distribution should have this form. Okay, so have this form, because that's what we got from prior distribution. So that distribution that has that form is called a beta distribution. Okay, so you don't have to worry about the mathematics behind this, but you just think of, I have this form, but in order to make it a distribution, I need to come up with some kind of coefficient so that when you sum them up, it's equal to 1. In this case, we take the integral for theta from 0 to 1, then it's equal to 1. So that makes it a probability distribution. So that constant happens to be this form. Okay, so don't worry about that one. It's just equal to, it involves a gamma function, gamma 4 times gamma 3 over gamma 5, and gamma n is just n minus 1 factorial. So that is called a beta function that has this distribution, that has a distribution in the same format or same form in our prior belief. So that we are going to use this distribution as our prior distribution. Okay, so then now I observe let's say I observe a new experiment. In this particular case, I have 3 heads, 3 tails. So then this is the new, so this is a PD of theta. That's what we observe. This is new. So theta cube times 1 minus theta cube, and times is a prior belief, that's theta cube times 1 minus theta square over B of 4, 3 PD. Now, this is a constant. So we can just, in order to maximize this thing, it's equivalent to maximize this thing. Okay, so to maximize this thing, it's just equivalent to, you look at how many heads. So you get 6 heads, and the total number of outcomes is 11. So it's 6 over 11. So that's what you get. And because we take the maximum value of this and we give a name to it, that's called a maximum a priori. So that's P as MAP. So this is theta is equal to 6 over 11. So that is the adjusted value of theta based on new observation. And that is a Bayesian parameter estimation. Okay. Of course, then you keep running more experiments, you may have to adjust this theta more. And at a certain point, if you don't have to adjust this theta, that means that this theta now converge to what it should be. Okay, and then you know what the underlying probability of of seeing head for this particular coin is. Right, it's a biased coin. But now we figured out what that theta is by running lots of experiments. At a certain point, you stop adjusting the value of theta, and that will be the value of that coin, the probability of seeing head for that coin. All right. So with this in place, now let's look at language models. As we said earlier, what we are interested in text mining is to figure out the probability of each word that appears in the underlying document. Okay, so then a language model is a probability distribution of is a probability distribution over word sequences. Okay, so I get to remove one of these things. It's a typo. Okay, for instance, probability of today is Monday, let's say, is equal to 0.001. And the probability of today, Monday, is obviously this doesn't happen often because this is not grammatically correct. So then, of course, it may happen in very, very small probability. Okay, this is so small, it's basically, it doesn't happen. You can think of that, doesn't happen. But it may still happen, even though it happens rarely. Okay, so a language model is context dependent and it's called generative model because we may use it to generate text. Okay, so it depends on context, obviously, it's easy to understand. And we can use a probability, we can use a language model to generate text, which means we can use it to generate words, right? So because we figured out the probability of each word, the probability of phrases like this, or some segments like this, then we can use them to generate text. So that's why it is called a generative model. So what we are interested in particular, is the following. Number one, predicting a word W by seeing a text W prime. Okay, so you have seen this so much, and what would be the next one? So because the next one could involve several different possible things, and then which one would occur most likely. So that means that we have to figure out their probability. So that means that we want to know the probability of a word W happens by seeing a text W prime. For instance, what is the probability of happy when you see John, when you see the following, John and feels. So that's the first thing we are interested in. The second thing we are interested in is to classify an article by seeing certain words. Okay, so classification really means that what this article is about, so which category this article could be put in by topics. For instance, if we see baseball 3 times and game once in the news article, then how likely is it about the topic sports, right? So it has a tendency that this news article is about sports, but we still want to figure out its probability. Number 3, we want to predict a query word by knowing users' interests, right? So let's say a user let's say you have a search engine, you observe Alice, the user, often clicks certain documents, and then of course, then you want to predict what queries would be in order to achieve these documents. Okay, so this is about text retrieval, right? So how do you retrieve a text document by making a query so that you retrieve what you really want to retrieve. So for example, if a user is interested in sports news, how likely is it for the user to use baseball in a query, right? So all of these will have to do with language model. In other words, all of these will have something to do with with the probability distribution of words, of phrases, of longer phrases, right? So such as today is Monday is a phrase. So this is called 3 grams. So you have 3 words together, right? So you want to figure out the words, bigrams, 2 words together, 3 words together, 4 words together, and so on. You want to figure out their probability. That is called language model. Okay. So the simplest language model is the unigram model. So what that means here is that we assume words are independent of each other, are generated independently. Okay, so that means that if you see a word or a sequence of words, W1, W2, Wn, then the probability of this to happen is the product of the probability of each word. Okay, so that is called unigram model. Likewise, you can generalize unigram to 2 grams, or sometimes we call it bigrams. So 2 words together, and excuse me, or 3 words together called 3 gram or trigrams, and so on. So given a language model theta, okay, so now this is theta now represent the parameter in a probability distribution for this language model. The maximum likelihood estimate of a unigram language model for a document D is straightforward. So we call that theta star. So you just count this W for each W, for each word W, because it's a unigram. So for each word W in your corpus, or think of W is a word in your dictionary. So for each W, it may occur in D or it may not occur in D. If it occurs in D, we count the number of times it occurs. So that's what C means. It's a count. Then it represents the number of times W appears in D. Then over the total number of words. You think of D as a multi-set of words because each word may appear more than once. So then if it appears 2 times, you count it twice in this size of D. Okay, so that's the size of multi-set, and multi-set of words is also called a bag of words, allowing each word to appear more than once. And you also count it. So that's the maximum, this MLE, that's the maximum likelihood estimate. Okay. In practice, of course, bigrams, or trigrams, or in general, n-grams with n greater than 1 are more useful because they capture more information of the text file or the text document. Okay, so let's just look at some examples I got from your textbook. So this is for one corpus, you get the following. Okay, so for each word under that model, for the language model, it may have a different probability. For instance, food here in this document is only 0.00001% using maximum likelihood estimate because it looks like this document is not about food, but this is because it has a very high probability, 0.25%, almost 25%. 0.25 means almost 25%. It's about food. It mentioned food, and then it mentioned nutrition, healthy diet, and so on. So this is about food and diets, right? And this is about definitely not about food. Okay, something else. So we don't know because maybe about text. This is 20%. Mining 1%. So it's about text mining. So this paper, this document is about text mining. This document is about food and nutrition. Okay. So that's application of this language model. When you figure out it's a probability. Okay, so next one. We can use a different language model to represent different topics. Well, actually, in the previous example, we already saw, right? So the different model actually represent different topics. The first one is about text mining. The second one is about food and nutrition. And of course, we can generalize that to a corpus of documents. So in this case here, so we have all these words. So again, you see computer, small probability, and food, larger. But here, computer has a larger probability than this one, right? So you look at all the words in the document, you look at their maximum likelihood estimate, and then you can use that information to classify this document. So again, this one also is from your textbook. So we can use topic language model and a background language model to find semantically related words. So here is the background English text, right? So this is background. That means you know that this article "der" happens a lot in any English text. Same here, right? So same here. They happens a lot. So A happens a lot. So these the A or is, so they don't really tell you much information about. So later on, we'll talk about that. These are in these stop words we can remove from text. So what's remaining that really gives you meaning is the other words, okay, such as food, computer, text here, right? So these will be some useful words. So again, we have this background document English text. So these, again, they don't really mean much, right? So the ones that mean much is these words, okay? So that's language model can do to us. So in this lecture, we talk about, we basically want to talk about language model. In order to talk about language model, we have to talk about how can we estimate the parameter in the distribution for the language model. Okay, so we talk about two methods. One is maximum likelihood estimate. The other one is a Bayesian estimate. And then we use a simple distribution called binomial distribution for coin tossing to explain that, these two methods. And for text, as we said, that we can think of words, or words are generated independently from throwing a biased dice of n faces, and is a total number of words and punctuations and digits. Okay, and so then the model for generating words, or a bag of words, is a multinomial distribution, right? Because it's not binomial, because you have so many words, so it's a multinomial distribution to generate a bag of words. All right, and then we talk about, once we know how to compute, let's say, a unigram model, then we can use it. So these are all unigram model. Then we can use it to classify documents. So that's it. So that's what we have, what I have for today. And what time is it now? Okay, so we have a few minutes left. So are there any questions?
No questions so far.
Okay, I read a chat from Brian. Brian asked whether there is a Discord server for this class. I don't know. I didn't set it up. Okay, so
yeah, would people like me to create that for us?
Yeah, sure. If you want, and just share our link to us, I'll join. I don't mind.
Okay. Okay, cool.
Okay, good. Yeah. Thanks, Brian.
Sure.
For doing this. Yeah. Okay. Any other questions? Okay, then I'll see you next Monday at 8:30 in the morning.
Thank you, Professor. Have a good day.
Yeah, thank you.
Thank you.